Okay, so a line, okay, if I were to actually draw a line, right, it's going to either like look like this, or it could fall down. It could be like flat across. It could go straight up and down, right? Those are all different lines, okay? So how do we notice that that's happening in a table? It's if you have the same constant rate of change, okay? Because your slope, lines have slopes. You're always going to go up 5/2, like between every single point, something like that, okay? If there's curves, right, your rate or your speed changes. But lines, it always stays the same. So with our first one, see how the width, that top row, goes 80, 100, 120, 140, 160? Okay, see how it's the same thing every time? Up 20, up 20, up 20. That has to also happen for my y's. Okay, so from 4,800 to 7,000, it's 2,200. Then what about 7,000 to 96? That's like 26, right? So is that the same? No, so guess what I can say? It is non-linear. So the first one is not linear. Good. Good. All right. Number 2, we have deliveries and hours worked. Look at the top row. 6, 7, 8, 9, 10. Is that going up by the same each time? Up 1, up 1, up 1, right? We're good. So my bottom needs to do the same. My bottom goes 8 to 8 to 8 to 8 to 8. Technically, you're just adding 0, right? So guess what? This is a line. Good. Technically, this is just adding 0. This would look like this guy. It would be flat because there's no change. Number 2 would be a horizontal line. That's what that's showing. All right. So, thank you for trying. This kind of gets you into like the mindset was the point of this warm-up. We're going to get in the mindset of, is it a line? Is it not a line? Okay. Is the graph continuous or is the graph discrete? So we have an either or kind of question we're going to ask ourselves. Okay. We're going to practice this tomorrow. We're going to do one more thing Wednesday with graphs. Practice that on Thursday. And we're going to do a short quiz over just these 3 sections. Okay. I don't want you to. Okay. So the first either or question is going to be, is it discrete or is it going to be continuous? Okay, so I want you to look at the pictures first, okay, because I'm a very visual person. I feel like y'all are too, okay? So look at my discrete graph. What do you see on my discrete graph? It's not a line. They're just dots, right? So discrete, dots, disconnected, okay? That all should go together to tell you it's a discrete graph, okay? So disconnected dots. Okay, so hopefully that little trick kind of helps you remember. Okay, look at the continuous one in the middle. How is that one a little bit different?
It's a U.
It's a U? Infinity? Yeah, my arrows. I got arrows on the end. Do you see dots being separated? No, it's a continuous flow, right? So these are connected. So continuous is a connected flow between all your points. Okay? There's no stopping at all. The last graph, it's none of the above. Okay? It's not one continuous graph. And it's also not individual dots. So this isn't going to be neither. Okay, it should just be dots or it should be flowy. If it's a mix of the two, it's not considered to be anything special. Okay, this is technically called a piecewise function, which we're not going to do until Algebra 2. So we're not going to learn that right now because it's pieces of functions is what it is. Okay, so in words, which is kind of what we just talked about, discrete are points that are not connected. So down there, this was our disconnected dots. That was the same thing we just labeled. Continuous functions are points that are connected to form a line or a curve. So I would underline connected. They're all connected to be continuous. Okay. And then to be neither, some points are connected by a line or a curve, but it's not going to be continuous everywhere. There's going to be breaks. There's usually breaks in your graph. Breaks or holes in the graph between lines or something like that. Sometimes when you get to algebra 2 and you do rational functions, where's that poster? It's behind CJ. It's that green one. Those have holes in them. So like you would graph it and actually stop and draw a hole and then keep going. Rationals come from fractions. So that would be if you divided by 0 is where that hole shows up. You don't have to worry about it. You're not going to do it, but that's where it would come from. Yeah, that shows a hole. Yep. All right. And then our second little table of information just talks about domain and range. So discrete functions, their domain and range is just the list of the points, which we did on Friday, right? Speaking of Friday, if you have that extra credit, make sure I get it before you leave today. Okay. So those first 2 problems that we did, we listed out the points. Some of you already gave it to me, and you're good. But if you were working on it over the weekend, make sure I get it today. Okay. So a domain of a discrete means you have remember that squiggle line, and we like wrote numbers. Like I'm gonna pretend 1, 2, 3. Like you actually wrote them out. And then with our range, we actually wrote out the individual values. So like, I don't know, 7, 12, 15, whatever they were, okay? Continuous functions, because they continue forever, their domain is going to be all real numbers. So you will forever go left, forever go right. Someone mentioned it earlier in the graphs, they had arrows. Okay, that shows it's not stopping. The range, it could be all real numbers, but if there's a turn, like we see in the graph, then it might be above or below a maximum point. And then the things that are neither are all over the place, and we'll deal with that when we need to. Okay, their domain and range is going to vary based off of what kind of concoction they give us. Okay, so ready to do some? How about now? A little bit. So we have an example here about books. The Bargain Book Barn sells young adult novels on a sliding scale. That is, the more books you buy, the cheaper they are. Let f of x model the store's prices for given quantities. Is f of x discrete or continuous? Explain your reasoning. So they gave me information as a table and as a graph. So looking at the information, would you call this discrete or continuous? Why? Okay. But look at my graph. Are they connected though? No, it's okay. It's okay. This one is going to be discrete. Because we have individual, there we go, values not connected. So we got to be careful with real world stuff. We got to make sure our math makes sense. So every time you have to think about the situation, okay? When I'm buying something, I can't buy half of a book, right? If these were connected, this shows that 1.5 books would cost me $2. That doesn't make sense. You're not going to buy half a book, okay? So that's why these aren't connected to each other. If you buy 1 book, this is the price. If you buy 3 books, this is the price. And like, that's it. There's no in-betweens, okay? So this is an example of discrete. Bonus question, would you call it continuous or not continuous? Does it show that it goes forever? This one would be non-continuous because it only gave me 5 points. And I can't do more than what it tells me. So that was just like a bonus question. All right, let's do more visuals. Okay, here we go. My first graph right here. Continuous? Yeah, how come? Yeah, we have the arrows, and it's nice and flowy, right? Everything flows in between. Good. Yeah, that one's continuous. What about the next one? Neither. Yeah, we got a bunch of pieces of something. What about the third one? Discrete. Careful. Yep. Discrete. It's okay. So we have dots, right? We have data points, so that's discrete. And then my last one, continuous. Good, that's a continued flow. I don't have an arrow on the beginning, but I do have one on the end, right? Okay, so that was the continuous or discrete part. The back is going to be focused on line or not a line. Okay, so do we have questions about discrete or continuous before we go to the back? What's up? Okay, you're fine. Okay. Okay, so on the back, a lot of words here that I'm going to condense down for you because a lot of words make my head hurt. Sure, it makes your head hurt too. Okay, a line is a function that has a graph that is a line. So if the domain of the function is all real numbers, then the function is continuous. Okay, a linear equation can be used to describe a linear function. Linear equations are often written in standard form. Okay, so let me show you what standard form is. It is ax plus by equals c. That is standard form. Okay, meaning something x plus something y equals just a constant. Okay, that is a standard form of a line. There's lots of different ways. You probably are also familiar with y equals mx plus b, right? That would be okay too. Yeah, the slope-intercept form. That's also a line, okay? Notice in both of these examples, you have just a y and just a x, okay? Meaning there's no exponents. I don't have y squared, I don't have x squared, right? It's just a y and just an x, and that's important, okay? That's important. It's nonlinear if I can't write it that way. If there is an x squared in my equation, not a line, okay? If it's missing an x or a y, that's okay. Okay, there's an example over here where it says x equals -3. That's okay. That's like saying 1x plus 0y equals -3. So that is the same thing as saying x equals -3. That would be good. That would be a line. I still have just an x with no exponent. All right, does that make sense? Okay, so sometimes you'll see all three pieces. Something might be missing sometimes. But that's okay. That just means that there's a 0 in its spot. Yeah, it's really bad. It's okay. Okay. Yeah, to check, like it's good. Like that's okay. But if it was like x squared equals 9, bad. Can't do it. All right. So we're going to give you functions sometimes that you're going to have to combine like terms before you tell me if it's a line or not. Okay, so the first one they're giving you is y equals -4, I'm sorry, not negative. Y equals 4x squared minus 2x in parentheses squared plus 3x minus 5. Okay, so with my order of operations, we have to do our exponents first. Okay, and we're going to do it to what's in the parentheses. So this ends up being y, come on, there we go, equals, I have 4x squared minus this piece right here. I'm going to zoom in. There we go. Both of those pieces get squared. So what is 2 squared? 4, and x squared is just x squared. Next part of order of operations should be multiply and divide if I see any, and I don't. And then after that, it's add or subtract if you see any, which I do. I see 4x squared minus 4x squared. They both have x squared. I can do that. So what is 4 minus 4? 0. So this becomes y equals 3x minus 5. Does that look like the equation of a line? It looks like your slope-intercept form, right? To make it standard form, you want your x and y, excuse me, on the same side. With the rearranging our formulas last chapter, we would just subtract the 3x over to move over here. So our standard form would be negative 3x plus y equals negative 5. These both show a line. So this is linear. Okay. This was slope-intercept form, and this was standard form. The main thing they have in common is that x does not have an exponent. Y does not have an exponent. That's the big thing you're looking at. So they both prove it's just a line. The pieces that had the x squared canceled out, right? 4 minus 4, it got taken away. How do we feel? Okay. He was just answering my question. Is anyone still writing that down before I move over? Okay. Determine whether 3x squared minus the square root of 9x squared minus y equals 17 is the equation of a linear or nonlinear function. Okay? So there's some simplifying I have to do before I can answer that question. Because I see a square root of 9. I can do that. You can do that. What's the square root of 9? 3. So I'm going to say this is 3x squared minus 3x squared minus y equals 17. Can we simplify even more? Yeah, I can combine like terms. What is 3x squared minus 3x squared? 0. They cancel out again. We're left with negative y equals 17. Is this a line? Yes. Technically, there's a 0x right here that we don't usually write, but it is there. So if I were to separate it, A is 0, B is technically negative 1, and C is technically 17. That is standard form. So is this a line? Yes. 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 This is the equation. My box is the equation, and my cloud is the answer. This is a line. Okay, so if you can label your A, B, C from your standard form, you're good to go. Like over here, A was negative 3. Over here, B was technically a 1. And C was a negative 5. All right, come back to this one. Make sure you got it. All right, we've done 2. We're going to do one more. And then after this, we'll do tables. Excuse me. We ready? Okay. Third one, you think? Okay, I have y equals 3x to the power of 3 minus x to the power of 3 plus 3x plus 6. Okay, so I don't have to like multiply or anything, but I do see like terms. I see 2 pieces with an x cubed. Right? Can we subtract those? So what is that going to end up being? 2, how'd you get that?
Because S3 minus S3 is the 1 in front of the x.
Technically, there is a 1 in front of this x to the power of 3. Good, Isaiah. So when you subtract those, that's where the 2 comes from. So we have 2x to the power of 3 plus 3x plus 6. Is this going to be a line? No, why not? What's the problem with it? Okay, I will tell you. It's right here. This exponent of a 3. That's the problem. I cannot have an x to the power of 3. That makes it a cubic function, not a linear function. You can't have any exponents. Okay. If you were to graph this, it would look something like this. Fun fact, that is not a line. Okay. So the other two before, my x squares canceled each other out. That was nice. Here, my x to the power of 3s, they didn't cancel out. So it's not a line. Ready for tables? Okay. So to prove if it's a line or not in a table, we need to prove slope. Okay. Line shows slope. Slope is the change of y divided by how your x's change. Okay. Rise over run. So that's what tables show us. Okay. All my phones need to go away. I see about 4 of them. Okay. You're fine. I know why you're. I can see your screen. I know what you're doing. If that's a problem, then we don't need to sit there anymore. Right? Right? Okay. We were having a good day. Let's keep having a good day. Here we go. In my warm-up, we checked to make sure that my x's were going up by the same, that my y's were going up by the same. Okay? This changes a little bit because look at my x's. -5 to -1 to 0 to 2 to 3. They're not going up by the same each time. Okay? It doesn't mean it's not a line. It just means that we have more work to do. So we're going to find their rate of change between the points. Okay? So again, we're looking for, this means change of my y divided by the change of my x. That's how we're going to find the slope. Okay? It does not matter which points you choose from. Okay? So y'all probably aren't fans of negatives, right? And that's okay. So how about right here? This y value from 0 to 6, how does 0 change into a 6? We added 6, right? That's a +6. All right, how did the x's change? How did 0 become a 2? We added 2. Now you actually divide. What is 6 divided by 2? 3, okay? We have to do it again. And if I get 3 again, I've proven it's a line. If I don't get 3 again, I've proven it's not a line. Okay, so let's just keep going. How does 6 become a 9? We're adding 3 again. Oops. And then how does 2 become a 3? You add 1. What's 3 divided by 1? So what can we say about this? It's linear. Yep, it is a line. Good. Okay, and that's because these were the same. Okay, they had the same slope, so that's why we can say it's a line. Right? We're going to do it again with our next one. My x's go 0, 1, 2, 3, 5, 7. So those last couple ones kind of messed it up, but that's okay. My y's, 0, -1, -8, -27, -125, -343. So we're going to do the same thing we did last time. Let's start at the top. How does 0 become -1? Subtract 1. Good. How did 0 over here become +1? Add 1. So what's -1 over 1? -1. There we go. There we go. All right, let's do it again to see if we get a match. How does -1 turn into -8? -7. And how does 1 become a 2? Add 1. What is -7 divided by 1? -7. -7. You were close. You just had your signs mixed up. Okay. Did I get the same thing? No, they are not the same, right? These are different. This is what we're comparing to each other. Not the same. So is it a line? No. Non-linear. Okay. They were different. Therefore, it's not a line. They're not the same. It's not a line. Questions for me? Okay. Here we go. Let's talk about a pool. Here we go. Fernando uses a garden hose to fill his empty pool. The table shows the amount of water in the pool after every 5 minutes. So first we're going to determine, is this a line or not? You think so? How do you know? How did you prove it? Okay, so we're going up 5, up 5, up 5, up 5. And over here it's going up what? Up 60 every single time. Good. So that proves, yes, it's linear. Okay, good. So we had a constant rate of change. It was the same thing each time. All right, now it wants me to graph it. Okay. So here we go. We're going to make our time our x values and our y's are gallons. 5, 10, 15, 20, 25. That's how I'm going to label my x values. I'm going to even label that axis as my minutes. And then my y's go by 60s, right? So I can go 0 to 60, 120, 180, 240, 300. And this is our gallons. I'm going to give you a second to get that down. I did label my x's as my minutes and my y's as my gallons. That's GAL at the top. There we go. Zoom in for you. All right, we said it was a line, so when I plot my points, I should hopefully see the shape of a line, right? 560 is right here. 10, 120. 15, 180. 20, 240, and 25, 300. Did we get a line? Yes, we did. Can I connect those dots? Yes, we can. Because it's continuously flowing or filling up, right? So I could connect them to each other. I'm not going to do an arrow because it didn't give me past that point. So you got to be careful. If it gives you data, you can only use the data that they give you. Because it can't really go forever because eventually the pool is full, right? We just don't know when that's going to be. So we stop with what they give us, okay? What's up? We're almost done. Stay with me. Almost there, okay? All right, the last little bit, we're going to review what we did. We're going to say linear or nonlinear, and then we're going to say continuous or not continuous, okay? Javier's weekly salary is the product of his hourly pay rate, which is $10, and the number of hours that he worked, okay? So if he's consistently making $10 each hour, is that a line or not a line? It's a line. It's a line. It is linear. Okay, that's the slope. The $10 was the slope. It's always going up 10 each hour. Is this going to be continuous or not? It can be continuous. Yeah, absolutely. For as much as he works, he's going to get money, right? And it doesn't jump. It's not going to go from 1 and then 2. You can work an hour and a half. Right? It's possible. All right, how about number 2? I have the points 1, 5, negative 2, 7, negative 5, negative 2, 4, negative 4, and 2, 1. You don't think so? Why not? Okay, but like, what if you plot them? What happens? Let's see. 1, 2, 3, 4, 5. So this is the first one, right? 1, 5. I'm just doing a little sketch. And then negative 2, backwards 2, up 7, 6, 7. Okay, so far we're good. Negative 5, 1, 2, 3, 4, 5. Oh, but then down 2. Uh-oh. So that right there also proves it's not a line. Okay, so you can start plotting the points. I don't have to keep plotting. That already there proves it's not a line. But if you wanted to, 4, -4, 1, 2, 3, 4, and down 1, 2, 3, 4 would be here, and then 2, 1 would be right here. So that would be the points plotted, and they're kind of everywhere. Okay, so this is definitely going to be nonlinear. Is it going to be continuous or not continuous? Not continuous, good, because it's a bunch of points. It's a bunch of dots. So it's actually discrete. We're going to get fancy. This is discrete. This is not continuous. This one is discrete specifically because of just the dots. All right, the area of a square, which is a times s squared. So now we're looking at the function. Is s squared the equation of a line? No, because of the power of 2, right? That's bad. I can't have an exponent of 2. So because of this, that makes it non-linear. Is it continuous or not? It is continuous. Okay. It didn't tell me how big the square was. It could be any value, right? They didn't really give me any data with it. I can plug in anything and get anything out of it. So it's going to go on forever. It didn't tell me it stopped. All right. We're good? Okay. Number 4. We have a table now. What do we think? Nonlinear? How did you prove it? Well, you got to prove it, though. You can't just, guess. Remember, we got to do the change of y over the change of x. So let's just make sure. How does 5 turn into 2? Okay, down 3. How does -1 turn into 0? It goes up 1. So what's -3 divided by 1? -3. Okay, we got to do it one more time. How does 2 become -4? Down 6. So from +2 to -4, you're going down so from 2 to 0 is 2, right? And then down 4 more. So down 6. All right, how does 0 become 2? You add 2. What is -6 divided by 2? Uh-oh. Uh-oh. It's -3. So are they the same? Yup. So what is it? It is linear. Yeah, that is correct. It is not continuous. Okay. Yeah, it is. This one is not continuous. How come? Yeah, it's a bunch of different data points, right? So we could even call this discrete because they gave me dots. They gave me data values, so it is not continuous. It only gave me 4 pieces of information. That's all we could plot. All right. My last one, is this continuous? First question, is it a line? No, nonlinear. Is it continuous? No, because there's a break in the middle. And look, it also has a hole. See that open dot? That shows a hole. So this is not continuous. Can I call it discrete? No, I cannot call it discrete. Discrete is just dots. Okay, discrete is just dots. So this one's not continuing. There's a break, and then that's it. It's not special. Okay, not continuous. There was a break. Good, hold on. Stop. Any questions for me? All right, I need stamp papers out.